Welcome to the Explainer. Today, we're putting on our detective hats. We're going to learn how to look at a bunch of numbers and figure out the real story hiding inside.
So let's kick things off with a bit of a puzzle. If you look at data from the 2000s, you'll find something, well, kind of weird. There's this almost perfect link between how much money video arcades were making and the number of computer science PhDs being handed out in the US.
And I mean, just look at how closely these things line up. The official number for this connection, it's called a correlation, is 0.985. A perfect score is 1, so that's incredibly close. It's so strong it's practically screaming at us, right? Hey, one of these is causing the other. But is it really? All right, so let's dig in. Because here's the thing. Numbers can lie. And as we're about to find out, a single number almost never tells the whole story. What we're going to do is build ourselves a proper data detective's toolkit so we can learn how to spot the truth and separate fact from, well, fiction.
Okay, tool number 1 in our kit. This is the first thing any detective looks for, a connection. In the world of data, we call this correlation.
Basically, correlation takes a whole, potentially messy relationship and boils it down to just one number. It's a score between -1 and +1. And this little number is actually super powerful. It tells us two really important things: how strong the connection is and which way it's going.
So a positive correlation, that means when one thing goes up, the other tends to go up too. Think about it, like height and shoe size. Taller people usually have bigger feet. Simple enough. And a negative correlation is just the opposite. When one thing goes up, the other goes down. Like, say, the more hours you spend playing a video game, the lower your battery gets.
But, and this is a huge but, this is where things can get really dangerous. If you just rely on that one little correlation number, you can get into a lot of trouble. This is probably the single most important thing to remember about this tool. You've probably heard this phrase before. It's like the golden rule of data. Correlation does not imply causation. Just because two things are moving together, it doesn't mean one is making the other one happen. And that is the giant flaw in our whole arcade theory. Yeah, they're connected, but one is not creating the other.
And just to show you how misleading that one number can be, check this out. We've got 4 different sets of data here. Now, if you only look at the statistics, they look identical. Same average, same variation, and, you guessed it, the exact same correlation score. So, based on the numbers alone, you'd swear they were telling the exact same story. But they're not. And this, right here, is why you have to always look at your data. You have to plot it, because when we do that, boom, 4 totally different stories. One is a nice clean line, another is a perfect curve, and the other two, they're completely thrown off by one single weird data point. The numbers, on their own, were lying to us.
Okay, so if correlation isn't enough, if it can lie to us, we clearly need a better tool in our kit. We need something that does more than just say, hey, there's a connection. We need something that can actually describe that connection and maybe even let us make some predictions.
And that brings us to tool number 2, simple linear regression. Now, don't let the name scare you. All it really is drawing the best possible straight line right through the middle of all our data points. It's like drawing a roadmap that shows the main trend. That line is our model.
Let's try this out with a real-world example from our source material. Imagine a social media company, and they have a question. Does having more friends on our site actually make people spend more time on it? I mean, it sounds logical, right? This is a perfect job for our new tool.
So we run the numbers, draw our line, and we get a new metric. This one's called R². And in this case, our R² is 0.329. What does that mean? Well, you can think of R² as the explanatory power of our model. It tells us how much of the story our line is actually explaining. So an R² of about 0.33, well, that means the number of friends a person has explains only about 33% of the reason they spend so much time on the site. Which, hey, that's something. But it also means that a whopping 67% of their behavior is a complete mystery to us. There's clearly a lot more going on here that we haven't even looked at yet. Yeah, the real world is complicated, right? It's almost never just one thing causing another. To get a real understanding, we have to look at all that complexity. So let's grab another tool and start building a much fuller picture. So what we do is we take our simple model, the one that only looked at the number of friends, and we start adding more clues. Let's throw in hours worked per day and also whether or not the person has a college degree. When we do this, we upgrade from a simple regression to a multiple linear regression. It's the same idea, just it can juggle more than one variable at a time.
And, wow, check out the difference this makes. By adding just those 2 extra pieces of information, our R-squared, our explanatory power, more than doubles. It jumps from 33% all the way up to 68%. Now we're explaining way more of the story. We just built a much, much better model.
But hold on. A good detective knows it's not just about throwing more clues at the problem. You have to add the right clues. Some of them might just be red herrings, leading you down the wrong path. So how do we check our clues? We use something called a p-value. You can think of it as a fluke detector. It basically tells you the odds that the connection you're seeing is just a random coincidence. And the rule of thumb is, if that p-value is really small, usually less than 0.05, it means your clue is probably legit. It's the real deal. So when we look at our model's results, the number of friends and hours worked variables, they have teeny tiny p-values. That's great. It means they're definitely important. But then look at the degree variable. Its p-value is 0.356. In statistical terms, that's massive. That's our fluke detector screaming, hey, this is probably just random noise, so it's a bad clue.
And what does a good detective do with a bad clue? You toss it. Get it out of there. So we remove that degree variable from our model. And guess what happens to our model's overall power? Barely a change. It's still just as strong. So now we have a model that's simpler, cleaner, and just as powerful. And that is the real art of this, finding the handful of things that actually matter and ignoring the rest.
So let's recap what we've put in our detective's toolkit today. We started with the basics, using correlation to just spot a connection. Then we learned the crucial lesson of always visualizing our data to see what's really going on. And finally, we moved on to building these powerful regression models that can actually start to make sense of the complex world around us.
So here's the bottom line. Data is always telling us a story, but it almost never tells us the whole story right up front. The goal is to be a good detective, and now you have the tools to do just that. So the next time you see a big statistic in a headline, don't just nod along. Ask yourself that one simple question. What part of the story are they not telling me?